This video is going to go start to finish through an example of the transportation problem. I'm not going to very slowly go through each steps. I'm just going to go through the entire problem. So if you need to stop and start the video as we go through to double check various steps, definitely do that. Okay. So the setup here is we have some button company. We're modeling 3 warehouses of the company that ship to 2 of its stores. In the chart, we've got the cost associated to shipping from each of these 3 warehouses to our 2 stores. So here to read this chart, the cost to ship from warehouse 2 to store 1 is $5 per unit. Okay. Now, in terms of over here, this tells us the supply of each warehouse. So maybe warehouse 3 has a supply of 30. Again, the units aren't really involved here much. This here is maybe it's 30,000 crates of buttons. Okay. In terms of store 1 and store 2, both of them have put in an order, or they have a demand of respectively 40 and 50. So first thing you want to do is you want to set up your initial tableau. I typically set up my initial tableau without an initial solution first and then add on the initial solution. The nice thing about being given a table of this format is when you set up your initial tableau, you're copying almost exactly the same table. And I'm going to go ahead and abbreviate warehouse 1, 2, and 3 with W's, and then the stores with S's, just to make my life easier so I don't have to keep writing tons and tons. Okay. So what do we see here? We see that for warehouse 1, we have a cost of 4 to ship to store 2, then 6, then 5, then 3, and so forth. We then look at our supply, and all of our warehouses have a supply of 30 units. And for our stores, we see that we have a demand of the 40 and 50 we saw before. So in terms of setting up your initial tableau, this would be the initial tableau. Now, once you have your initial tableau, then you're ready to go ahead and put on your initial solution. So here we use the northwest corner method, and remember, north means reading up the table and west means to the left of the table, so you're always looking as high up and to the left as possible. So here we see our first cell is 1-1 that we can use. The warehouse has a total supply of 30. The store 1 has demanded 40. Well, warehouse 1 can't supply that full demand, but it can supply 30 units, which means store 1 still has to get 10 more units from a different warehouse, and warehouse 1 has fully been depleted. Notice at this point in time, warehouse 1 cannot ship to store 2 since its supply has been totally depleted. So then we look back again, and using the northwest corner method, we look for the next cell, so as high up as possible and to the left as possible. So now we're looking at cell 2-1. So here we're still at store 1. This warehouse now has what? It now has 30 units, but store 1 only wants 10 more units. So we're going to go ahead and put in 10 units that warehouse 2 is going to ship to store 1, and that goes ahead and says that store 1 is completely dealt with. Okay. Now we then at this point we see that warehouse 2 still has supply. Store 1 is depleted in its total supply. So store 1 isn't going to be getting anything from warehouse 3 because it's got everything it wants. So now when we apply the northwest corner method, notice we're only in column 2. So here we look up and we see, hey, in cell 2-2, store 2 is demanding or wants 50 units. Warehouse 2 only has 20, so we'll go ahead and ship 20 units to store 2 from warehouse 2. This then totally depletes warehouse 2, and store 2 will have some of what it wants, but not everything. At this point, there's only one cell left in your tableau. Both the row and the column of that particular cell I've left 30 units in both the supply and the demand, so that tells us our 30 units is going to be put in the last cell. And notice here, if you've done it right, you'll have zeroed out all of your supply and all of your demand. It's completely used inside of this tableau. Now, most people don't normally put in those highlighted bits. I like to put in sort of like a grayed out area. If I was doing it with a pencil, maybe a line through those cells just to indicate that, hey, we're not actually putting anything in the cells. And this would be the initial solution. Okay, so if somebody ever asks you, initial tableau with initial solution, this would be the answer right here. Now, note, because we didn't actually explicitly say it, before you can apply your northwest corner method, you do have to go ahead and make sure that you have a balanced tableau. Here are total supply and total demand were both summed up to 90, which meant we were already balanced and we did not have to add in a fake store. And without scratch work, this is what that initial solution on that initial tableau would look like. Now, at this point in time, we could totally calculate the current cost. So cost of the initial solution. And the cost of the initial solution is simply take each of the values of your cells, the values that are explicitly written in there, and multiply it by the associated cost of that cell. And this will turn out to be the total cost associated with this particular way of transporting, in this case, your buttons. Once you finish multiplying all of the values in each cell that has a value by their cost, you add them together and you get the total cost to transport the goods along the edges associated with these cells. Notice also this means that every time we adjust or attempt to improve our solutions, every future solution needs to be this same cost value or less. If you ever get to an iteration where your cost, if you calculate this at each step, if your cost goes higher, that means you did something wrong. So that's a quick way to check your work. Now, once you have your solution, whether it's at this first stage of the initial solution or if it's any of the iterative steps in the future, what are we going to do? We're going to calculate our sale prices. So these are the prices, and these are only on our solution variables, otherwise known as the basic variables. Okay. So for these guys, remember the formula we're using? Is just going to be cost minus the V, cost equals V minus U. Whether you remember what the V's and the U's stand for doesn't matter. Okay, one of them stands for the selling cost at the store and the other one the price at the warehouse. But at the end of the day, it doesn't actually matter if you remember what these U's and the V's are. These are just some scratch work to help us figure out which of these cells that we're not currently using, so that one and that one, the two that are blank, which of those cells would actually cause the largest decrease in the cost to ship your product. Okay, so here we're going to look specifically at our solution cells. So we're going to look at the cells that actually have values in them. So that's cell C1, that's cell C21, that's cell 22, and cell 32. We'll then go ahead and apply the formula to each case. So the C1 equals V1 minus U1, C21 equals V1 minus U2, and so forth. We then take the cost associated with each of these cells and plug it in. So in the first cell, first cell 1, 1, we replace the C with a 4. The second cell 2, 1, replace the C with a 5. Next cell C2, 2, we replace the C2, 2 with a 3. And the last one we'll go ahead and plug in the 8. At this point, we're ready to solve for all of those U's and V's. You always set U1 equal to 10. Technically, you could set it at any value, but we're going to set it to 10 because it'll make your life easiest in terms of solving for these U's and V's. You then just work your way through each of these equations and solve for the remaining guy. Notice if you start off with equation 2 right here, you wouldn't know either V1 or U2, so it wouldn't be very helpful. So always proceed to the next equation where you already know the value of one of these to either U or V. This is why we had to start off by setting U1 equal to 10, because we had to be able to start somewhere to actually solve for one of the two values of U and V. So here, V1 would equal what? That would equal 14. Why? Add the U1 to the other side. So now we know these two guys. Next one down, we already have a V1. So we just plug in V1 and we're going to be able to solve for V2. So here's 14 minus something equals 5. So that looks like a 14 minus 9. So U2 should be 9 here. Then we say, all right, well, we move down to the next one. We don't know V2, but that's okay because we do know U2. U2 is 9, so we move 9 to the other side, so this is 12. And the last one down here is U3. Notice U3, we have V2, which is 12. 12 minus something is 8. So 12 minus 4 is 8, which gives us our U values. Okay. Now, what do? We're now going to take this information and use it to figure out what's going on with our non-solution cells. So our two non-solution edges or non-solution cells are 1, 2. So we'll look at the adjusted costs on cell 1, 2. And we also have 3, 1. So we'll also look at the adjusted cost on cell 3, 1. At this point, we just apply the formula and plug in. Remember, our formula here is exactly the same formula we used before, except we have the one adjustment factor at the end, which is subtract the actual cost. So here, we already know the U's and the V's and the C's from the given. So we'll go ahead and add these in. So this looks like it is 12 minus 10 minus 6. And that looks like it is what? That looks like a negative number. That looks like a negative 4 right there. So next what happens? We'll plug in V1, which is 14, U3, which is 4, and then the C31. C31 is 6. So this guy looks like we are getting a positive 4 right there. Now you compare the two edges. Remember, a negative actually means the total cost will increase. A 0 means no change whatsoever if you switch out and use that cell. And a positive number right here means that if you actually use this cell, your total cost is going to increase by 4 units per, well, however much you throw through that edge. So here, what does this tell us? This tells us that we need to add to our solution the edge or the cell 3, 1. So this guy is going to be our new cell that we add in. Well, the next thing that we want to do is every time you add in a cell, we're then going to have what? We're then going to, in fact, form a cycle in your underlining spanning tree. So you have to identify who's the loop in the tableau, which corresponds to the underlining newly formed cycle in your spanning tree. Well, remember, as soon as you get a cycle in your spanning tree, it's no longer a spanning tree. It's, well, not even a tree. So what we do here is in the actual tableau itself, we're going to go ahead and find that loop. So if we look in the first column, no help because we have two choices. But if we look in this last row, well, there's exactly one choice that we can go to. And remember, those cells in your loop are always the new cell you want to add in and cells already in the solution. Now over here in column 2, we look up into column 2 and there's only one other possibility in terms of somebody who's already in the solution. So that has to be cell 2, 2. And then that means we know who our fourth cell is. So that now is our loop in our tableau. If we write this out, this particular loop is exactly those 4 cells. Now, not everybody likes to write out the loop. I always recommend when you're first starting to always write out the loop, and that's because one of the things we have to calculate is which cell of the loop is considered an odd cell versus an even cell. Remember, you always start with your new cell, and that one's always going to be tagged even. Once you know that this start of the cell is even, everybody else is going to alternate odd, even, all odd, even. You then need to go ahead and calculate your theta. And your theta is always going to be the minimum of the two values or of the values on your odd cells. So 3, 2, 3, 2, the value is 30. And here, the other odd guy is cell 2, 1. So here the value on cell 2, 1 is 10. You compare the two values and you grab the smaller of the two values. The smaller of the two values is the one that is going to correspond to the cell you kick out. If they're different, if they're the same, you get to pick. Okay. So what happens with this value? Let's use purple. what we're going to do is the value of the new cell we add in is always going to be that theta value. So here it's going to be 10. Now, on the odd cells, you subtract off this amount. So here we're going to subtract off 10, and here we're going to subtract off 10. Notice going both directions, one cell along the loop you subtract, and then across the cell, this is the one that you add in. Okay? So that's how this guy is going to get adjusted. This also tells us which cell is going to get kicked out. Notice here, cell 2-1 is going to zero out. It's the only cell on the loop that's going to turn into 0. So that's the cell that we're actually going to remove. So let me go ahead and write this over to the side. Remove cell 2-1 from our solution. Now, once you have that next iteration, the quote-unquote better solution, and note we can calculate the cost associated to this guy. So notice, just like before, we multiplied the values of the cells that were actually visible times their associated cost, and then we just add that up. So we get that the current cost is $4.30, and remember the previous cost was $4.90, so we did in fact drop cheaper cost. Okay. Now, every time you get to this stage where you have a new solution, we do the exact same step we did previously. We're going to calculate our prices. We're going to find the new non-solution edge that will decrease our price. We'll use our loop to adjust, and then we've got our new solution. So let's do that next. So here we notice that the cells in the solution are 1, 1, 2, 2, 3, 1, and 3, 2. So I went ahead and pulled those subscripts for our cost, plugged into the appropriate formula that we use. And now the only thing that we have to do is, well, the U's and the V's we don't know yet, but the cost we do, so we'll replace all of these C's with the little label at the top of each cell. So now we're ready to solve for the U's and the V's. U1 we select to be 10. That's our default. We're always going to select U1 to be 10. Once we have that U1 equals 10, we can solve for everybody else. So in this scenario, we see that if U1 is 10, in order to have this equation satisfied, this tells us that V1 must be 14. Now at this point, we don't know either U2 or V2, so I'm going to skip that one. But down here in the next equation, I do know what V1 is. It's 14. So 6 equals 14 minus something. So in this particular case, what happens, I'm going to go ahead and do this guy next, which tells us that U3 equals 8. Now let's double check that I did that math right. 14 minus 8. Yep, that does give us 6, so we're good there. So we've dealt with those two so far. Now, up here, we're still looking at V2 and U2, so I don't have either yet. So what does this tell us? This tells us still have to skip that equation. So coming down here at the bottom, what do we have? We now have a V2 and a U3. Oh, well, we have U3, so we can totally solve for V2. So U3 equals 8. So add that to the other side, and this tells us that V2 needs to equal 16. Now that we have V2, we can come back up here to this second one. V2 now equals 16. 16 minus something equals 13, which tells us U2 has to be 13. Now we've got all the background information we need in order to select which of these cells which are currently not a part of the solution, which of those two guys should be thrown into the solution to make the total cost reduce or decrease. So here our cells are 2, 1, 2, 1, and 1, 2. So I wrote them both down already. We're just going to use the appropriate formula and plug in all of the values that we already have. So we see that V2 is 16, U1 is 10, and the cost in cell 1, 2 is 6. So this looks like we get an adjusted cost of 0, which tells us, yeah, you could throw in that edge 1, 2, but it's not going to change this overarching cost, so there's no point in doing it unless you really wanted to. Now, in the other cell, so here, if we threw in that edge, what would happen? The change in the cost would be V1. V1 is 14. U2. U2 is 13, and the current cost in that cell is 5, so minus 5. And notice you can visibly see without actually adding it up that this is going to be a negative number. So that actually tells you if you go and throw in that cell to 1 that we had in the past, that will actually go and increase our total cost. Now, as soon as we have the fact that both of those two cells give you a change or adjusted cost of 0 or a negative value, this tells you that the current solution is the optimal solution. So current solution is optimal. In other words, this one provides the smallest cost possible. Now, we actually went ahead and calculated this smallest cost already. So let us go ahead and look to see what this optimal solution would look like if you wanted to write it out. Okay, so optimal solution, you would write out all of the x's. So here x11 would be, you can just barely see it at the top of the screen there, so let me scroll down just a hair. Oh, it's not letting us. So this would be 30. And that's at a price of $4 per unit. Actually, sometimes these guys are also written where this is really something like $400 per something unit. Sometimes they put the dollars in units as well, as in scaled units. We have a 30 units, warehouse 2 to store 2. This is at $3 per unit, or we'll ship at $3 per unit. We also have the cell 3-1, so this means you're going to ship 10 units of buttons across the edge, warehouse 3 to store 1, and this is at a price of $6 per unit. And then lastly, almost off the top of the screen here, warehouse 3 to store 2, so this is subscript 3-2, and that looks like there's 20 units that we want to ship across, and this is at, let's grab that price, this unit price here is 8. Okay, so this here is your optimal solution. Now, one of the things you're typically asked is what is that minimal cost for our particular transportation problem? What do? You just multiply all of these together and then add them up. And just as a heads up, all the other values of x, the ones that are not explicitly given or stated or written out, these two guys would be 0. Well, we already multiplied all these together, so we found previously, before we realized that that was our optimal solution, that we got a price here of $4.30. So I'm just going to go ahead and write that down. This price is $4.30. See work above. And if we put this all back together in the bipartite graph, notice what happens. I didn't bother to go ahead and include all of the edges from the complete bipartite graph, only the ones we were going to use. From warehouse 1, we only are shipping to store 1. Warehouse 2, only shipping to store 2, so this tells us the full 30 units at the price go to store 1. Same deal here. And warehouse 3, which had the higher shipping cost, first we used the lowest shipping cost possible, but warehouse 3 with the higher shipping cost, we actually went ahead and used it even though it did have the higher shipping cost. But we used it to fill in the gaps when warehouse 2 and 1 and 2 weren't able to meet the full demand of our two stores. Okay, so this would then be a picture representation of this optimal solution right here. But that's it. That's the transportation problem.